All right. So again, we're going to continue with chapter 3 on which deals with descriptive statistics. And where we ended up last time. Talked about the center of the distribution last time. Now we're going to talk about the spread of the data. Let me know if it doesn't move forward. I think it will. Make sure of that. Some of these things that we'll be talking about are very, very straightforward and simple, but I'll show you how to set it up also in Minitab, so you can do these things. So the first one is called the range, and it's actually the distance between the smallest and largest value. So you basically subtract those two values, and that is called the range. Now, can somebody tell me whether this type of calculation is a good calculation for determining the spread of the data? Do you think it's a really good one? Just give your opinion. Okay, Han, you have an opinion? No, not a good. So tell me why. Why don't you think it's a good measure of spread?
I think it only counts the two data from a set, the largest one and the smallest one.
Yes. Oh, Rose. Okay, hold on a minute. There's Rose. Okay. All right. So we're good now. So Rose, you just changed to your personal. Okay. All right. So yes, you're absolutely right. It only deals with two data points, and it says nothing about what's happening in between, the spread of the data in between. So it's okay, but it's not great. Now, one thing I want to mention to you guys about spread. If all the data points were exactly the same value, there was no variability between the data points, then would you agree that the measure of spread should be 0? Would you all agree with that? In other words, if all the data points had the same number, let's say the data had 10 numbers in the data set and they were all 5s, would you agree that the spread is 0?
Yes.
Right. So one thing that you should always think about when you're dealing with spread is that the minimum value for the spread is 0. It can't be negative. All right, it's 0. Now, of course, you never see that, basically, right? Because there's always some variability in the data set. But just realize that whatever we choose as our measure of spread has to have a minimum value of 0. And is that true in the case of the range? Is the minimum value 0?
Yeah.
That's right. And that would be the case where all the numbers in the data set have the same value, right? So the largest value would also be the smallest value. And when you subtract them, you get 0. So the range is a valid measure of spread. And then any other type of variability should have a positive spread, correct? Should be positive. And the more variable the data is, the bigger the spread should be. The spread calculation should be, right? I mean, it makes sense, right? That's how you would determine if there was more spread, because the positive number would be bigger. So keep that in mind when we go through these things. With the range, yes, if the distance between the largest and smallest value got bigger, you would say yes, there was more spread, but it won't. But it only be the spread between those two numbers. Again, it says nothing about the spread in between. So it's possible that you could have two data sets that have the same range, but would have different spread, right? Because you could picture, for example, a data set with a large number and a small number, and then all the numbers in between are the same number that are in between. That wouldn't have much spread, right? It wouldn't have that. And a data set that has that same large number, the same small number, but more everything in between is more spread out, the spread value should be bigger because the middle is more spread out. So I want you to think about data intuitively too, not just, formulas and calculations. I want you to think about it intuitively. So let's get to the next one. Now, in this book, they kind of take an advanced turn with this in terms of the definition here. Typically, if you find the mean of any data set and then take the mean and subtract it from every data point, the difference between the data point and the mean of the data set is typically it's called deviation from the mean. Makes sense, right? Deviation from the mean. So if the mean is 5 and one of the numbers in your data set is 7, 7 minus 5 is 2. 2 is the deviation from the mean for the number 7. Okay? Now, in this case here, they're also calling it a residual. Residual. Now, why do they call it residual? Because later on in the course, when we talk about regression, that is, we're looking at two variables, the relationship between two variables, and we create what's called a scatter plot, right? That have an XY points, a bunch of XY points. And we want to draw a line through those points. The difference between the value on the Y value on the line and the actual Y value, we're going to call that a residual also. So, but don't get confused about that now. I think it's unusual for them to use this term here in the book, but just know that residual in this particular setting means deviation from the mean. All right, that's all it means. And notice that if we have a population of data values, we see X minus mu, because mu is the population mean. And if it's a sample, then it's X minus X bar, because X bar is the sample mean. Remember, for population, we use the term parameter, and the parameter for the mean is mu. That's the population mean. We use the term statistic to refer to a mean, in this case, for a sample. So X bar is the sample statistic. All right, so just know the parameter refers to populations, statistics refer to samples when we use these terms. Now, let's just go back to the deviation from the mean. Here's something that you should always know. If you took the deviation from the mean for every number in the data set and added up all those deviations from the mean or residuals, added them all up, you would always get 0. Okay? Makes sense, right? It makes sense that the sum of all the deviations from the mean, or the sum of the residuals, whichever way you want to call it, is always going to be 0 for any data set. Now, is that a problem when we're trying to measure spread? If we always add up the deviations from the mean, I mean, we are taking into account every number in the data set when we do this, right? When we add up all those deviations, we're considering every number in the data set. It's not like the range where there's just 2 numbers that we're looking at. We're looking at every number. If we added up all the deviations and we get 0, is that a problem for the calculation of spread? What do you think? That's right, Steve. You're absolutely right. It is a problem because remember, this measure of spread has to get bigger as there's more variability. And if you add up all the residuals and they always add up to 0, then that's not a good measure. That's a bad measure of spread. So what do statisticians do? Well, the reason why when you add up all these deviations you get 0 is because they sort of cancel each other out, the deviations. Some of them are going to be positive, some of them are going to be negative. What if we take the deviations and take the absolute value of them right? You take the absolute value of them and add up the absolute value of the deviations, then they won't cancel each other out. And that's where this measure comes in, the MAD measure, mean absolute deviation. I don't see this used very often. It can be used, it's fine. It's not bad to use it. But I think the reason why it's not used is because for people who are not mathematically astute, they don't like that, those two bars there, that absolute value thing kind of makes it look more complicated than it is. So they sort of like, nobody really took this seriously, this one here, because they thought, it's just too complicated. But it works. And it is a valid measure of spread because the bigger the spread, the bigger this MAD number will be. Okay? And it has a minimum of 0, doesn't it? So what do? How do you calculate it? Well, for a population, you add up the absolute values of the deviations and then divide by the number of numbers in the population. For sample, same thing. We add up all the deviations from the mean. In this case, we use X bar because it's a sample. And then we divide by small n because small n is the number of values in a sample data set. All right? And that's what it is. That's all it is. Again, and not used very often. I mean, I don't see why it couldn't be used, but it's not used. All right. The more typical one is called the variance. Now you might say, wait a minute, I like that MAD one, right? This looks more complicated than MAD one. Well, for some reason, people like this, all right? For some reason, people like it. One reason is that many years ago, before they had computers, you could take the numerator of this formula and create this numerator, and it would be equivalent, all right? If you did the math, did the arithmetic here, the numerator here and numerator here are equivalent to each other. And it used to be when we didn't have calculators and we didn't have laptop computers, that this was easier to calculate than doing absolute value. All right, adding up all the absolute values, this was easier to calculate. So that's probably the reason why they did this, because it computationally, and also when we did get computers, this was easier to program, probably. Well, this is called the variance. And what is the variance? Well, we take our deviations, instead of taking the absolute value to turn them all positive, we're going to square them. We're going to square them. And whenever we square a negative number, it turns positive, doesn't it? So this is an alternative to the MAD statistic. We're going to square the deviations and then add them all up. And for a population, we divide by, again, the number of values in a data set. Now we use this Greek symbol, sigma. Now this sigma here, see this symbol up here, the one that looks like an E, right? That is big. That's the big capital sigma. And the Greek letter down here is small sigma. So this is also sigma. But just like in English, there's capital letters and there's small letters. So this is called sigma squared. Sigma squared is the variance for a population. Is the variance a valid measure of spread? Yes, because the more spread there is, this value goes up. And it does take into account all the numbers in a data set, because you're adding up the deviations squared for every number in the data set. Sigma squared is and the way I would call this, I would say the sum of the squared deviations from the mean, or the sum of the residuals squared divided by the number of values in a data set. And that's called the variance for the population. Now, what's really odd is when you take the variance for a sample, the numerator is pretty much the same, except we use x bar instead of mu for the mean. But look at the denominator. We don't use small n, we use small n minus 1. And there is a technical thing about why we use n minus 1. There's a thing called an unbiased estimate. Unbiased estimate. We want to make sure that what we calculate in a sample, which is not the entire population, it's a subset, is a unbiased estimate of the population value. And it's a technical thing. I'm not going to go into it, exactly what it means, because we would have to get into mathematical statistics, which involves calculus and all of that. So you'd have to have a calculus background. So maybe you do. Maybe I could talk about it if this was more of that type of course. But just for now, just believe me that dividing by n minus 1 makes this an unbiased estimate of the population variance. So for beginning students, this is sometimes hard to remember that they have to subtract 1. So I keep repeating it over and over again until students remember it. So it's the sum of the squared deviations from the mean, or the sum of the squared residuals divided by the sample size minus 1. When I use the term sample size, the word size is referring to the number of members in the sample, the number of observations in the sample, okay? Sample size. Population size is this big N, all right? So this is the variance. And again, it has a shortcut thing here. I don't think we need that for this course because you have your calculators, you have computer software. These shortcut formulas aren't necessary. All right. Any questions about variance? Valid measure of spread. Now, can somebody, let's see how well you are paying attention. Can somebody tell me why this is not the final step in calculating spread? What is it about the variance that kind of throws things off a little bit? There's something not quite right about the variance. So let me
Squared?
The square thing. And what does that do? What does the squaring do? You're absolutely right, Han. It's the idea of squaring, but what does the squaring do?
It made the spread look bigger than it actually do.
Correct. And that's a very good point. That's exactly right. It makes it much bigger than it really is, right? Unless the spread is decimal, then it makes it smaller. But yes, it makes it much bigger in most cases than it really should be. But there's another reason too. Think about the way we measure things. That's your hint. The way we measure things. What does squaring of the value do in terms of measurement? I don't know how I can say it in any other way without actually giving you the answer.
Is it about negative and positive?
No. Because the negative and positive has more to do with the deviations, right? I mean, it's possible the x's are negative, right? It could be. We could have negative numbers there. Think about measuring something. Let's say we're measuring height in inches, height of a person in inches. What does squaring do? Mo and Rose, are you there? I don't see your
I'm
pictures.
here. Sorry,
Okay.
remember my camera's broken.
Oh, that's all right. It's all right. That's Mo, right? Talking? Mo?
Yeah.
Okay. How about Rose? Are you there?
I'm here too.
All right. When I don't see you and I don't hear you, I don't know if you're there. Here's the answer. In terms of measurement, the units of measurement get squared. So inches squared becomes the units of measurement in a variance formula. Is that really, if we're measuring somebody's height in inches, does inches squared make any sense? It doesn't, right? That's a measure of area, right? It's not a measure of height. So what do you think we need to do to get it back to its original measurement unit of inches? What do we have to do to the variance to get from inches squared back to inches?
Square root.
Square roots, exactly. And that's why the variance is not the end all of the measure of spread, because the units of measurement get squared, and we have to take the square root of that number so that the units of measurement return back to the original units. And that's what we call the standard deviation. That's why we do the standard deviation. And if you look at any computer printout of anything that we measure, it's always, always standard deviation. You never see variance. The only reason you learn variance is so that you know where the standard deviation comes from, right? You calculate variance first and then the standard deviation. So this is the point right here. It says it right here. Since the variance is in squared units, we have to take the square root of the variance to get the units back to their original units. So sigma, small sigma, in this case, sigma, is the measure of population standard deviation. You can see why they put a 2 in the exponent for variance, so that when you take the square root, you end up with plain old sigma. All right, so sigma is our population standard deviation. And for a sample, remember the sample variance, they used a letter S squared for the variance. I didn't bring that up to your attention before, but just like in for the mean, we use English letters for the sample statistics. We do the same thing with the variance. So we see S squared for the sample variance, and then when we take the square root, we end up with S as the sample standard deviation. All right? So these are the types of things you sort of will get used to seeing over and over again, because you will. This is a big part of the course right here, is just learning some of this, this notation. All right? So standard deviation is the end-all of most spread calculations. Now there are some variations of the standard deviation, but this is the one that's most often reported. Now, there is one more before we get to this. This one here. I want to go back. In the book, I want to bring this to your attention. See if I can find it. On page 70 of your book, after they talk about the range, they also talk about this calculation called the mid-range. Now, I don't see that used very often, but I do want you to at least know what it is. And the mid-range means that you take your two ending values, the smallest and largest value in your data set, and you average those values. You average those values. So instead of subtracting them, you're going to add them and divide by 2. And mid-range sometimes is used of the center of the distribution, just like the mean and the median. All right? Because what you're doing is coming up with some number in the middle, right? That's really what you're coming up with. Again, I don't see very many people using it. It might have been used many, many years ago, maybe 100 years ago, 50 years ago, who knows? But it's not used that often in today's world. All right, so wanted to bring it to your attention. Will I ever ask you about it? It's possible, but it's so easy to remember, right? Because mid means sort of middle, doesn't it? You see mid-range, that sort of should give you the clue that it means at the average of the two numbers that are used in the range. All right, so this one actually can be useful. I don't see people use it very often, but it can be useful. Called the coefficient of variation. Now, why would we want to do this calculation? Because what it is basically is you're going to take your standard deviation and divide it by the mean, and then multiply it by 100. So it's actually a expressed as a percentage. And what it is, it's sort of a relative amount of dispersion relative to the size of the mean. Why do you want to do this? Well, because if you were comparing two groups, maybe you're measuring the same thing. Maybe you're measuring height. And maybe one group is the height of lady gymnasts. Lady gymnasts tend to be relatively short in height, right? They might be very strong. One of my daughters was a lady gymnast. She won New Jersey competition when she was young for being a gymnast. But she's 4'10". And that's that typical height for a gymnast. You know, being tall as a lady gymnast is 5'2", 5'3". And then you have lady basketball players, some of whom may be over 6 feet tall. Well, the numbers are bigger, right? The numbers are bigger for the lady gymnasts in terms of inches than they are for the lady basketball players than they are for the lady gymnasts. So if we talked about the spread in absolute terms, like the standard deviation, the same standard deviation in absolute terms for those two groups would mean something different, wouldn't it? For smaller numbers, it's going to look relatively large, right? It's going to be relatively large for the small numbers, and it's going to be relatively smaller for the bigger numbers. So if you have the same standard deviation, two distinct groups, it would be better if you were going to compare them to divide those standard deviation values by the mean, all right? And it would make it more of an apples to apples comparison. So this is what they call a relative degree of spread. And what happens to the units here? They cancel each other out when you divide them, don't they? So this is unitless. So it doesn't even matter what the units are, they get canceled out. And we're left with something that can be compared between two groups. And it's called the coefficient of variation. And again, I don't see it used so often, but to me, it's a very useful tool to have if you were going to make comparisons between unequal groups. All right, any questions about that? Just don't get it mixed up of what goes in the numerator and what goes in the denominator. Always think of this coefficient of variation as a measure of spread. And therefore, the numerator is always going to be the standard deviation. All right? It's just being divided by its corresponding mean so that it comes up to a relative measure of spread. Now, the next slide is what we're going to start covering next time, which is relative position. All right? We're going to talk about quartiles, percentiles. We're going to talk about a graph called the box plot. And these are used all the time. But this takes a little bit of time to go through. So I'm going to have that next Tuesday for this topic here. Okay. So for the rest of our time here, we have about 15 minutes or so. I think I'm going to go into Minitab, playing around with Minitab today. So let's share it. And where are you, Minitab? There you are. Okay. Now, on page 75 of your book, like they seem to do in every section of the book, they have a computer exercise to illustrate what was learned in that section. So this is a example of using Minitab for these calculations. So one thing I forgot to do, and I should have done it, And I think I'm going to do it right this second. So, and I apologize. I should have posted this data set that I have here on Canvas. Oh, I can't minimize. Jeez. That's not good. All right. I think you should just watch it. Try it on your own when we're home. And then, unfortunately, I can't minimize unless, well, oh, you know what? Maybe I can still do it. Let me click this. And I think it's still being recorded. All right. You just won't see what I'm doing. All right. I'm going to go into Canvas and post the data set that I'm going to use so you can follow along. Just give me a second. Any questions so far while I'm doing this? No? Are you there?
Yep.
Can you okay, just want to make sure. All right. So it's still recording. Okay. And it should just take a second for me to load this file. All right. All right, so this is chapter 3 data set. It's CX03HOUS. It's the first one here. All right. Let me post it for you. All right, so I just posted it. It's the one that ends with HOUS. So if you are following along, it should be under this week's module. All right, and it's still recording. Okay, good. All right, here we go. So this is housing starts. This was something that was published by government agency for a certain year, and this is for, I believe, all 50 states. I think there are 50 of these here. Let me just verify that. Oops. Here we go. Yeah. All right. Anyway, I think they're in thousands or something. I'm not really sure, but it doesn't matter. This is our data set. All right. Now, what did I do? What is this asking to do in this page here? It's asking us to calculate a couple things. We need to calculate the range. Let's see what else. The variance, the standard deviation, the range, the MAD, coefficient of variation. I put skewness in here just for the fun of it. Mid-range, things like that. So let me minimize this. And let me show you. Now, of course, I just did the basic statistics, like descriptive statistics. And then what I chose was, this is the wrong one here, shows housing starts. And then for statistics, I picked the mean, standard deviation variance, the median. I think I picked that. What else did I pick? Minimum, maximum, the range. It actually calculates the range for you. And some, the number of values in the data set. I think that's pretty much it. And then you click OK, and you end up with this. All right. So the couple things that it does not calculate, it doesn't calculate the mid-range, and it doesn't calculate MAD. Now the mid-range is really easy, right? C2. I'll go back to calc. Again, use your calc. And let's just do mid-range again. C2. And I'll just tab down. And it was very easy, right? I just took the maximum value and added the minimum value. I added these two numbers, 271.4, 1.2, divided by 2, and that's your mid-range. Easy, right? Easy. All right. Variance. Now, they give you the variance here, right? 224,7855. They calculate it for you. But I decided to calculate it using Minitab the long way, all right? Because I wanted to see if this variance here is the sample variance or the population variance. Remember, the denominator is different, correct? For the population, you're dividing by n. For the sample, you're dividing by n minus 1. So the sample variance will always be bigger than the population variance for the same data set, all right? You have to know, of course, which one you're using. So I did a little test in C3. I decided to calculate the sample variance. I thought it might default to that, all right? So I'd hit calculator, and this is in C3, so let's just scroll over to 3, tab down, and I did this calculation here. And this is the formula for the variance for a sample. Now remember, there's 50 numbers in a data set, right? 50's here. So I did a sum, and I took the housing starts, the individual values, and I subtracted the mean of them and squared it, right, by doing this caret 2. And then divided the sum of that, of those square deviations, by 49, which is 50 minus 1. And I ended up with a match to what they showed as the variance here. So what they're showing you in when you calculate it, when you check that box, they're showing you the sample variance. Excuse me, let me. Sometimes I forget while I'm talking. Now, if you wanted to calculate the population variance, right, what you could do, what you would do if you were doing it the long way is divide by 50. Okay? You would divide this by 50. Instead of 49, you put 50 in there because there's n is 50. And then you get something a little smaller, right? Because you're dividing by a bigger number. Now in the book, it shows you how to convert a sample variance to a population variance. So if now that you know this is a sample variance, if you wanted a population variance, what would you do? You would multiply now since the denominator for the sample variance is n minus 1, right? You would multiply this number by n minus 1 divided by n, right? If the denominator of this is 49, and you want to make the denominator 50, you take this number and multiply by 49 divided by 50. The 49s will cancel, and you're left with the numerator divided by 50. All right, so this value is 24,785. You just multiply it by 49 divided by 50, and you'll get your population variance if you needed that. If you knew that the data set was a population and not a standard deviation. So the reason I'm telling you all this is that if you're going to be using Minitab to calculate the variance or the standard deviation, and I tell you in a problem, and what I always do, I always will tell you whether it's a sample or population by making it bold and underlining. All right. All right. So you know what you're dealing with. So you now know how to convert the variance for a sample into the variance to a population, or in term, for the same data set. All right. Does that make sense? Everybody clear on that? All right. Now, the standard deviation is the square root of the variance. This is the sample standard deviation. Now, because the standard deviation is the square root of the variance, then the denominator of the standard deviation formula is the square root of n minus 1. Right? If the denominator of the variance is n minus 1, the denominator of the standard deviation is the square root of n minus 1. So if let's say you didn't calculate the variance, suppose you were given the standard deviation, and you know it's for a sample, and you need to find the number for the population, then you multiply this number by the square root of n minus 1 divided by n, the square root of that ratio. And that would give you the sample, the population standard deviation. You have to remember to multiply by the square root of that ratio. Because in the original variance formula, it doesn't have square roots in there, right? No square roots. But the standard deviation is the square root of the variance. You have to have the square root of that ratio to convert this number to the population number. Make sense? Mm-hmm. Okay. And that's just a little shortcoming here. I'll have to play around with Minitab a little more, see if there's any way to convert from sample to population, whether it does that or not. But my initial experience with it is that it doesn't do that. So you have to, and the reason is because Minitab typically only deals with samples, right? In a professional setting. Mm-hmm. You're only going to be doing sampling. You're not going to look at everything in the population. But in an intro statistics course, sometimes you're being given to find the population values. So again, I'll look some more, but I just wanted to bring that to your attention. And on the bottom of page 75, they show you the conversion formula. It says it right below the 3.2 solutions for the Minitab thing. It's right below there. You see it. All right. Just a couple more things I wanted to show you before we leave. The range, 270.2. Of course, I calculated it to verify that it's the same, and why wouldn't it be the same? Now, the math calculation, again, Minitab doesn't do that, but you can do it with Calc. So I have that in C6. So let me show you that, what it looks like. Hopefully, I did this correctly. Oops, sorry about that. C6. There it is. So what is it? It's the sum of the absolute value of those deviations, right? The sum of the absolute value, that again, ABS comes from absolute value here. So the sum comes from here for the functions, the absolute value comes from here, and then you just put your deviation formula in here, and you divide it by what? 50. Now, MAD is always calculated with a denominator of 50, with n, never with n minus 1. All right? It doesn't, there's nothing about the MAD formula being an unbiased estimate or anything like that. So they just use 50. They don't use n-1. And it's used, that formula is the same whether it's a population or a sample. All right, and that's how I came up with that formula. Again, I will probably post this so you can play around with it yourself. And coefficient of variation, very easy. How do I get the coefficient of variation? I take my sample standard deviation, this number here, and I divide it by what? The mean, right? And the mean is in right here, 34.65. Okay? Or I can do it as a formula, right? I can do it as a formula. It's in C7. Change that to C7. And that's exactly what I did. I just said sample standard deviation, which is, I already calculated it, divided by the mean of the housing starts. And again, of course, you multiply it by 100 because it's a percentage. Another option is just to calculate this and change the column to a percentage. And it automatically express it as a percentage instead of a decimal. But I decided just to multiply it by 100 so you know it's a percentage. And the 143.7 is saying what? It's saying that 49.78 is 143.7% of the amount of the mean. Okay, that's what it means. Almost 1.5 times as big. All right, any questions about that? And then the last thing I did, and this is just for your own, I'm not, and would never test you on this, the skewness calculation. I was wondering, let's see, do I have skewness? I didn't even put skewness here, but I calculated skewness. Wait a minute, here we go. Here we go. I calculated skewness in this one here. Now, by the way, coefficient of variation is calculated, and I said it wasn't, but it is calculated in the statistics. So I apologize for that. I did, it is here. Hold on a minute. All right, there we go. And where is it? The coefficient of variation, right here. See it? Coefficient of variation. It is calculated here. You just check that box, it gives you that. So I apologize, it is there. But the MAD is not. That is not an option. The skewness, I wanted to see how they calculated this because I sort of knew what it was, but then the formula that I'm aware of didn't give me this number. So I actually looked it up, and again, this is only for those of you who are interested in knowing how to calculate it. It's this really, really long formula. All right. Instead of squaring the deviations, you're cubing them. All right. And then you're dividing by the cube of the population standard deviation. That's why I have it listed here. The population standard deviation. You're cubing it. You're multiplying it by the n. And then you're also, and this is all in the denominator, you're taking the square root of this adjustment here. This is n times n minus 1 divided by n minus 2. This is the square root of n times n minus 1 divided by n minus 2. You don't need to know this, but this is the way, I looked it up. This is how it was matched up, and this is how they calculate skewness in the Minitab. It wasn't what I got originally, and I figured it out, and there it goes. So, does it matter? Probably not. But I'm a geeky person, and I got kind of upset that the numbers didn't match. So anyway, so that's why that's there, in case you're interested. Now, I also did 3.22. This is the last thing we'll do today. Problem 3.22 is on the next page, 76. I give you a small data set of 8 numbers. The 8 numbers are, it's a sample of 8 apartment buildings in Chicago, and these are the percentage occupancy rates during a recent month of these 8 apartment buildings. So these are percentage of occupancy. And what did I do here? I did my basic statistics and displayed, right? Again, occupancy rates, and then I picked everything I felt like I wanted. So what did I pick here? I picked the mean, standard deviation, the variance. I did pick the coefficient of variation, so I did have that checked. The minimum, the median, the maximum, the range, and also I put skewness in there also, just for the fun of it. All right. Now the mid-range, of course, is not calculated either, right? So I calculated it here. And how did I find it? I just took the maximum value and added the minimum value and divided by 2, and I got 61.5 as the mid-range. Now compare it to the mean and the median. The mean is 34.65, the median is 18.3. It's not even close to any of those two, right? And that's why people tend not to use the mid-range. For the same reason, people don't tend to use the range, because it only involves 2 values in the data set. The mean uses all the values in the data set. And it's always the one that's preferred is the mean. All right. The median uses the middle value, right? But the data set's ordered and you find something in the middle. One thing I want to mention about the mean and median, if you have a very skewed data set, that is positively skewed or negatively skewed, the mean is not considered to be the best measure of the center anymore. You would use the median. All right. The median is, I did mention this last time, the median is not affected by outliers, and the mean is. So a skewed data set typically has outliers, and that's why we want to use the median as a measure of the center instead of the mean. Does that mean people typically do that? I don't see people doing that anyway. They still use the mean, but that's what you should use. But the mean is always preferable because it includes all the data points in the data set. All right, and then the calculation for MAD is here also, which I did, 9.125. The problem did ask, if you look at 3 points, it did ask for the mean, the median, the range, the mid-range, the MAD, standard deviation, and the variance. Okay. The one thing you notice here is the mean is bigger than the median and skewness is large, right? So this is definitely right skewed. And again, if you want to double check that, right, to see, you can go to, this is it right here. Actually, wait a minute. Did I do something wrong? Yeah, you know, I was looking at the wrong one. This is it. Duh. Han, you didn't catch me making that mistake. I had the wrong one up here. This is the one. This is the occupancy. Yeah, I was looking at the wrong one. I was looking at this one, housing starts, and this is the occupancy rate. So anyway, this is the correct one. N is 8. All right. Now take a look at the mean and the median. The median is now bigger than the mean, and the skewness is negative. This is the first case where we've seen negative skewness, right? And again, if you want to look at the histogram of it, does that look like it's negatively skewed? Well, sort of, because of this big one right here, right? You can picture sort of drawing a curve and then it just leveling off to the left. So it's left skewed negatively skewed. Okay. What else do we see here? Nothing in particular. There's nothing in particular here that's unusual. But it gives you everything you need for that problem. And then again, I added the skewness because I always like to take a look at the curve, see what it looks like. All right, that's it. Any questions about this? No? All right. I'm going to hold off on any homework until we finish the next section, and then I'll give you some homework for the entire chapter 3. I'm also going to come up with a quiz for the first, for this chapter number 2 on graphing. Something for you that we can do maybe next time.
We'll do it during class?
Yeah, I just want to, maybe or maybe not, I don't know. It depends on, actually, we lost people. We lost somebody, didn't we? We have everybody here? Oh, Mo and Rose. Oh, I'm sorry.
Still here.
Rose, are you going to be here
Yeah.
with us next Tuesday?
I believe so. I still don't have my schedule yet for next week.
Would you let me know?
Yeah, I'll let you know.
Yeah, send me an email because it'll be a very short quiz. All right, it'll be really easy, but I did promise 6 quizzes for this semester, so I want to give you a quiz in chapter 2 and one on chapter 3. Again, easy, just some basic, really basic stuff. So you'll have your book in front of you. Believe me, it'll be easy, an easy grade for you. All right, so don't be alarmed. I'm not going to make anything difficult for you for the quizzes. All right, I just want to make sure that you're keeping up with the work. That's why I do all this stuff. All right, and then the quizzes. I don't think there's enough vocabulary to do a vocabulary quiz, so it would be basically give you some graphs and just ask you a couple questions about it. Things that have clear answers. All right, nothing more than that. All right, guys, any questions about anything?
One very quick question. Is it okay, the homework, if it is submitted like as a document file with like any
Yeah.
pictures that are just, embedded into it?
Yes.
Okay.
You can
All right.
absolutely do that. And then in the future, when we do a project or something, you're going to be definitely embedding graphs or whatever, or charts, and then writing something also, writing something up. I might be asking a question. So you would submit a Word document that has all of that in there. So let's
Okay.
we'll take advantage of the ability of Minitab to import into Word or cut and paste into Word.
Yeah.
And then, yeah. So yeah, you can just do it that way. That would be fine.
Sure thing. Okay.
Yeah. And if you wanted to, I think, Han, maybe you had submitted also the project file too in the last homework.
Yes.
Yeah, that's
The
okay too.
Minitab?
That's okay too, because that tells me how you came up with the stuff. All right. So if you want to submit both a Word document and also the Minitab project file with your name on it, you can do it that way too. That way there's a backup to see, I can see how you came up with something if there was any question. Okay? Good. And Mo and Rose, did you submit your homework?
Yep, I emailed it to you.
You did, okay. I haven't had a chance yet to look at the emails. So was that Rose or Mo who just talked? I'm not sure. I can't see either one of you.
That was Mo.
No. How about Rose? Did you do your homework?
Yeah, I'll be emailing it to you.
All right, good. All right, good. All right. So guys, that's it for tonight. I don't know what happened here with the recording. I'll stop the recording. I will post this recording